Hello everyone. Let's look into another reason that leads to crosstalk noise, and which is lower supply voltage leading to lesser noise margin. So this is a quite exhaustive topic. So what we have done is we have just briefly summarized this one over here, and in the following videos, the videos which will be coming right after this one, in those videos we have explained in detail about the noise margin and about the how the lower supply voltage affects the noise margin. Okay, so this is how it looks like when we had a process which was for like 0.25 micron and above process. The supply voltage that we were providing was 2.5 volts, was close to 2.5 volts. So out of this 2.5 volts, some certain section of the voltage is referred to as noise margin high, and certain section is referred to as noise margin low. So what does this essentially means is that any signal, any rising edge signal, if it falls in this particular area, if the voltage of that particular signal falls in this area between VIH and VOH, it is referred to as logic 1. Okay, and any signal which falls in this area, whose voltage falls in this area between VIL and VOL, it is referred to as logic 0. So that's why whenever we have a voltage and we can't determine, or the logic or the gate cannot determine what is it voltage, it just detects the voltage of the signal, and checks whether that particular voltage level lies somewhere between here or somewhere between here. If it lies somewhere between here, it is referred to as logic 0. The gate, the logic gate, it detects it at logic 0. And if the voltage level lies somewhere between this, the logic gate detects it's at logic 1. This is how it works. This is how basically, because of so many disturbances, because of so many variations on the chip, you can you in an practical situation, it is practically impossible to get a logic 1 steady signal or to get a logic 0 steady signal. So there will be some amount of disturbance, there will be some amount of noise that is present. So in order to filter those noise, in order to filter, the gate has this property of noise margin. Every logic gate comes with a noise margin of itself. So whenever we say that whenever, let's say this is 0 volts, from 0 to let's say VOL is 0. So let's push this particular line at 0 volt, and VIL is some number, let's say out of 2.5, maybe 10%, let's say 250 millivolts. So any signal which is lying between 0 and 250 millivolts, that would be referred to as logic 0. There could be disturbances, there could be some ground bounds and reasons like that. We will be explaining all those in the following videos. So any kind of disturbances which is present between 0 and VIL, or between 0 and 250 millivolts, that is referred to as logic 0. Similarly, whenever the input of the logic gate is at logic 1 voltage, and let's say VIH is some number, let's say 10% of 2.5. So if you subtract 2.5 minus 250 millivolts, it will be 2.25 volts. So any particular signal whose voltage level lies above VIH, which is above 2.25, and lies below 2.5, that is referred to as logic 1. Okay, so this is the noise margin concept, and how, and this is what the noise margin is about, and these are the values. These are the rough values that we are just taking as an example in, let's say, 0.5 micron and above process. And always the noise margin are decided on a percentage of the supply voltage. Let's say in this case we took 10%, that's why VIL was 250 millivolts. In this case we took as again 10% of 2.5 volts, which came down to 2.5 minus 250 millivolts, which is like roughly 2.25 volts. So between 2.5 and 2.25 volts lies your noise margin high. Between 0 and 250 millivolts lies your noise margin low. This is just an example, it's a percentage of VDD. Now when we go for a process which is 0.1 micron and below process, the supply voltage itself that is being used is 1 volts because of various reasons, because of the device, MOSFET device itself, because this much voltage is actually sufficient enough to drive a MOSFET which is whose gate length or whose channel length is less than 100 nanometers or less than zero point 0.1 micron. So this much amount of voltage is pretty much enough for this particular MOSFETs to work. Okay, that's why the overall, and there are other reasons as well to reduce the supply voltage. One of the major reason is the power. So once you reduce the voltage, the amount of power dissipation that is provided by that particular circuit, the amount of static, dynamic, and all kinds of power dissipation that we have learned in some other videos. So those power dissipation is reduced when you actually reduce supply voltage. So there are several reasons for this. There are pretty exhaustive reasons for having the lower supply voltage for 0.1 micron below and above process, and power is one of those reasons. Okay, so once you have VDD equal to 1 volts, now what happens here? We had taken 10% of 2.5 volts, so it came down to 250 millivolts. Same thing if you apply over here, if it's like 10% of 1 volts, it will come to 100 millivolts. So if you see, once you reduce your supply voltage, the margin actually got reduced. The margin got reduced from 250 millivolts to 100 millivolts. So now what will happen is, in the older technology, if there was a, let's say, ground bounce, if there was some bump in the supply voltage, and the bump height was, let's say, 110 120 millivolts, so this particular technology node will recognize that as logic 0. And this particular technology node, since it's 120 millivolts, which is greater than 10% of 1 volts, that is 100 millivolts, this particular technology will detect that particular signal as noise. So you see, the amount of noise that will get accumulated in lower node is pretty huge. Anything that goes above 100 millivolts will be considered as noise. Here, anything above 250 millivolts, it's considered noise, but anything below 250 millivolts, it's not considered as a noise in a process which was 250 micron and above process. So that's the problem that we have when we go to lower nodes. We have to reduce the supply voltage because of power reasons, as I mentioned already, and because of that, the noise margin over here and over here, that gets reduced. So for example, you have 100 millivolts at the bottom. Basically anything that lies between 0 and 100 millivolts will be detected as logic 0, but anything that crosses 100 millivolts, that will go into undefined region. When I say undefined region, it means basically noise. It doesn't know either it has to go to logic 1 or logic 0, and it will go to either logic 1 or logic 0 depending on the state of the circuit at that point of time. That's why it's an undefined region, and it might actually break a circuit. For example, if an AND gate, let's say an AND gate expects, if the input of the AND gate expects a logic 1 and it gets a logic 0, the complete following circuit at the output of the AND gate, that will get deteriorated. Basically it's a functionality failure that we have. That's why this is the reason, and this is a very important, most important reason that we find that leads to crosstalk noise, and we have to find out a way to fix this. So we have ways to fix all these problems that we are seeing, but the major reason that we identified over here for that leads to crosstalk noise is the noise margin. Basically this is directly related. It's like it's a tolerance level that you have. If the input voltage at logic 0 is it's less than 100 millivolts, then the gate has no problem. If the input voltage lies between let's say 1 volts and 900 millivolts, then there is no problem. But if it lies somewhere over here, that is above 100 millivolts and below 900 millivolts, that's a concern for us. Okay, so these are some of the major reasons that we identified behind crosstalk noise. So what we'll do is, now let us try to take some example, take some real industrial practical example of crosstalk glitch, and do some kind of analysis to it. So all these concepts, all these things that we just learned about crosstalk noise, the reasons that we identified behind crosstalk noise, everything will be pretty much clear with the example that we will be taking over here. So what we'll do is, let me try to bring the example. Let me try to brief you about the example. So we will have this inverter, and this inverter will be driving another inverter through a chain of wires, through this particular set of wires. And since it's a it's a physical wire. A physical wire will have some cross-sectional area, and anything which has a cross-sectional area will have got some amount of resistance to it. That's why we have mentioned a small resistance over here. Okay, so this is one of the small circuit, and this we will be calling it as aggressor. This particular set we will be calling it as an aggressor, and this net we will be calling it as an aggressor net. Why? We'll be learning that very soon. Basically, you will infer by yourself that why it is called as an aggressor. And there is one more net that will be coming. So this will be one more inverter which is sitting very close to this guy. This one more net which is sitting very close to this net. And there is one more inverter which is followed by this inverter. So, and these two inverters are connected by again a piece of wire. And this particular net we will be calling it as victim net. Okay, so very soon we will be inferring the reasons why we call it as a victim and why we call it as an aggressor. Right now the scenario is that this net and this net are sitting pretty close to each other. Now let's see what happens, and there are other assumptions as well, that the aggressor drives strength and the victim drive, and all those things. We'll be looking into all those very soon. For now, let's leave you with that note that we have this particular scenario, and we have to identify the crosstalk glitch and the crosstalk noise in this particular example. So let's try to look into all this in the next video. Thank you.